Hey folks, in this video we're going to be talking about the basics of energy and matter because it matters. Get it? Ha, terrible joke. So I want you, dear viewer, to be able to explain the law of conservation of mass and also the law of conservation of energy. We got to follow these laws, and whether or not you choose to, you will. They're laws you kind of have to obey because the universe enforces them, not your local municipality or larger governing bodies. I also want you to be able to define particle theory because that's a really interesting thing that we can use to view the world. And I want you to be able to describe different classifications of matter, stuff that we're going to be interacting with. Matter. It matters. Yeah, so let's get going. Talking about this conservation stuff. I'm into conservation, conserving resources, and conservation of mass is one thing that I have to do because it's a universal law. And so this states that mass can neither be created nor destroyed, at least inside of a closed system, and I'll talk about a little loophole around that. But mass can neither be created nor destroyed. This is one rule that we kind of have to follow. So in any reaction, the mass of the stuff you start with is always going to equal the mass of the stuff you end with. That stuff might get dispersed or take different forms, but whatever mass you begin with, you must end with in a closed off system where things can't escape. Yeah, and so we also have conservation of energy. Conservation of energy, you might have guessed it, is that energy can neither be created nor destroyed, at least in a closed system where we can't have new energy getting in or energy getting out. And so this means that energy can only really get transferred between different things and into different forms or types of energy. So we could think about energy coming in this form of chemical energy. It might be radiant energy, aka light, like the stuff that is coming out of the screen that allows you to see this pretty face. And there's also stuff like electrical energy, which is undoubtedly powering the screen and allowing the transfer of electrical energy into radiant energy, so you can see my pretty face. Yeah. And so we can actually have mass and energy get interconverted. So if mass gets destroyed, we can kind of end up with energy. There's this funky law that Einstein, I think, came up with. I don't know. I know I associate it with Einstein. I don't know who to actually attribute this law to, and I'm not going to definitively say it's Einstein because I'm not sure. But it's E equals mc squared. I know that is the equation. And that's energy is going to be equal to mass times the speed of light squared. So you could theoretically convert mass into energy. And this sort of happens with my friends photons, but I'm not going to dwell on that right now. Because typically we do not see mass spontaneously converting into energy or the reverse, which is good because things might just start like exploding. Anyway, examples of conservation of energy and mass. Let's look at some examples right here. So if you got 10 grams of wood and you mix that with 100 grams of air, I don't know, maybe in some sort of closed system like a box, an airtight box, and you burn that mixture of wood and air. What's the mass of all the soot and all the gases and all the other stuff that's going to be produced? What's that going to weigh? Think about it. Ponder that for a second. Okay, well, it's going to equal 110 grams because you put 110 grams in together, and no matter what, you can't create or destroy mass. So the mass of all the things that you make from burning that wood and air together must weigh 110 grams. That would be conservation of mass, my dudes. All right, well, what about this one? If we got a light bulb, and that light bulb gets zapped 10 joules of electrical energy, and it shoots out 8 joules of radiant energy, what's going to happen to that remaining energy? Pause the video maybe and think about that. Okay, cool. Well, let's talk about it. Light bulbs, in my experience, get hot. I've touched a few light bulbs in my day. So that tells me that there's probably some thermal energy going on in there. If things are getting hot, that means there's some thermal energy present. So I can go ahead and just make an assumption that maybe those remaining 2 joules will have become thermal energy. You know, they could have been dispersed in other ways, but I'm just going to, say this to keep it simple because we have to conserve stuff. So if I put 10 joules of electrical energy into a system, that there's 10 joules in there, and only 10 joules can really come out at that point, if that's all there is. My 10 joules can't just be destroyed. We gotta send them somewhere else. All right, another example. I got a reaction. I got 2 chemicals, A and B, and it produces 88 grams of some sort of product. Doesn't matter what it is. Well, if there's 22 grams of chemical A that were used, how many grams of chemical B do you think I used in this reaction? Pause the video and think about that. Well, you done thought about that. Well, if 88 grams was on the product side, if I mashed up two things and got 88 grams of product, and one of the things I mashed up was 22 grams, the other one must be 66 grams, because 66 plus 22 gives me that 88. I wish life were this easy for a chemist, because it's not. You will produce 88 grams of stuff, but you may not get to keep all of it because you may lose some of it, as is life for a chemist. I'll talk about the sadness of being a chemist in another video. Yeah, but that would be the law of conservation of mass. If you make 88 grams of stuff, that means you must have been using 88 grams of stuff to make that 88 grams. 88 grams, it's all you get in life. Anywho, let's talk about this interesting thing called particle theory. What is particle theory? I don't know, maybe pause the video and think about that right now. Well, you done thought about it a little bit. And particle theory is a model. It's also sometimes called the kinetic theory. That's not exactly it. But I like particle theory because it's a nice simple name. And it basically states that all matter can be represented by many, just so gosh darn many, tiny, so tiny little particles. Like I am made up of all these little particles, little bits. We'll talk more about that. But these particles are constantly moving. And the amount that they move is determined by mostly two different things. The amount of energy those particles have in them, energy, and also their interactions with neighboring particles. You can't see them, but there's somebody standing right there, and there's also somebody standing right there. And I interact with them. No, I'm just kidding. But particles will interact with their neighboring particles. We'll look at that hopefully in the future too. And the particle theory is really nice because it's helpful for us to visualize the behavior of matter. Stuff that's like, atoms are too small for us to actually see, but the particle theory gives us a way to imagine how they're behaving. And it's really useful for us thinking about how solids, liquids, and gases differ. And, let's take a look at that right now because I love this little simulation guide. That's not the one I want. That's my screencasting thing. This guy right here. We can see this little goober is showing us these different states. And so in a solid, we can see even in a solid, these particles that make up a solid are jiggling around. And if I were to click this liquid guy and turn them into a liquid, we can see that they're jiggling around a lot more. There's a lot more movement in there. And we can also see that as a gas, these particles are no longer chilling together in a glob. They're just like moving all over the place doing their own thing. We'll look more about this, more at this in class later. But it's really nice that we can use particle theory to visualize the way different states of matter behave. And speaking of states of matter, it's really also useful for visualizing the changes in states of matter. For instance, if a solid becomes a liquid, aka melting. It's also really nice for visualizing chemical reactions in which we have these complex particles that are going to interact together and exchange parts so that they become new particles. Wow! And also for things dissolving, which I want to talk a little bit more about later. But let's talk a little bit more about matter, because I was just like, all matter is made of particles. But if you're like, hey bro, what's matter? Then we got to talk about that. What is matter? Pause the video and think about that. Well, matter is all stuff that has mass, aka weight. They're not exactly the same thing. But if it's helpful to think about it that way, then you do it for right now. And it's stuff that also takes up volume or space. Stuff takes up space. I can't put this jar inside of my body because we both take up space. We both have volume. We can't occupy the same space. So that tells me that this cup is also matter and that I matter. I matter. And so basically everything you're going to interact with ever is going to be made of matter, except for electromagnetic radiation, aka radiant energy, aka light, the visible light that's coming out of your screen right now that allows you to see my pretty face. Yeah, and so how we will find matter out in the world? Well, matter, we're going to find it in a few different forms. We'll find it as pure substances, and so this is when we have just one chemical, and we can't break it down into separate little bits unless we start doing chemical reactions, breaking bonds inside of it. Got an itchy nose right now. And so an example of this might be table salt, pure sodium chloride, at least in the solid form. That's not the best example, but whatever, no going back now. And so another example that's even better would be pure H2O. If you want to break this apart into hydrogen and oxygen, you got to do some chemistry on that, son. Yeah, and so you also might find mixtures out in the world. These are probably going to be a little bit more common, and that's when you have multiple chemicals mixed together, but you can separate them through some simple physical processes, as opposed to chemical reactions where you actually manipulate the bonds. And so we're going to find mixtures in two different forms, really. And those inside those two different forms, there's even more subcategories. But we have heterogeneous mixtures, and that's where you can see the individual little parts of your thing. And I need an example right now. This is a really bad example, but my example is a charger inside a jar, and it's a mixture of charger and jar, and you can see the charger. Anyway, so sand is an even better example, because when you look at sand up close, you can see that there's lots of little bits in there that are different. You can see all these individual little parts that are unique. As this is opposed to homogeneous mixtures, where you can't see the individual parts. It all looks the same, even though there's multiple things in there. And so another beach-themed example of this would be salt water. When you look at salty water, assuming it's like just, you know, some salt water, maybe you filter it to get some schmutz that isn't salt water, but that's going to be salt and water, which are both pure substances, but they mix together to make a homogeneous mixture. Very nice. Very, very nice. Well, here's some examples of matter, and I want you to ponder, are these going to be pure substances, or are they going to be mixtures, and are they going to be homogeneous or heterogeneous? Why don't you ponder that right now? Pause that video and think about it. All right, sick, you thinking about it? I thought about it too. What type of matter is a tree? Well, I think about trees, and they've got bark, they've got stuff on the inside, there's roots, there's leaves, there's all these different unique parts. So I would call them a heterogeneous mixture. You can start to break a tree apart into different unique things. Yeah. What about Coca-Cola? Well, if you get some Coca-Cola, that all looks like you pour out some Coca-Cola, the whole thing looks the same. So I know Coca-Cola is many things because it's got ingredients on the bottle, and I would call that then a homogeneous mixture, because it's many things mixed together, but when you look at it, you're like, I could not separate the phosphoric acid out of this. What about paperclip? What about paperclip? Think about that. You already did. Well, I would call a paperclip, most paperclips at least, a pure substance. I would say that they're usually just iron. Though we could get fancy and be like, well, that's stuff mixed into that iron. So, but if it's plastic coated, I would definitely not call it a pure substance. If you had a plastic coated paperclip, what would that be? I would say that that would be heterogeneous, because I've peeled the plastic off of a plastic coated paperclip. And what about brass? What about brass? Well, you might say brass. Brass is a metal. It's on the periodic table somewhere. It would be a pure substance. But brass is actually a homogeneous mixture. It's a mixture of the pure elements copper and zinc smashed up together. Here's a bunch of taco cats. I know this video is getting long, so here's some taco cats to break it up. And did you know that taco cat is a palindrome? As is one of my favorite palindromes, now sir, away, a papaya war is won. Anyway, enough of that silliness. Let's talk about this last thing I want to get on, and that is solutions, an important type of homogeneous mixture. So solutions are one or more chemical, dissolved into another chemical. And they are rampant around here, let me tell you. This typically, when we talk about them in chemistry, refers to a chemical dissolved into a liquid. And that's usually going to be a solid or another liquid that goes into a liquid. Look at here. I have some water that I can use for an example. Thank you, water, for being a wonderful pure substance. Well, water is actually really nice for making solutions. For instance, salt water would classify as a solution. It is sodium chloride dissolved into water. And so in this case, we have, in any solution, we have a solute. That's the chemical that is dissolved. So that would be sodium chloride in my example. And we also have a solvent, the chemical into which the solute is dissolved. That would be water in this case. Water is really good at dissolving things and is sometimes referred to as the universal solvent, but it definitely doesn't dissolve everything. So that's a crap lie. Anywho, water, good at dissolving things. Solutions are used frequently in chemistry, but also in everyday life. I'm going to talk about a few at the end of the slide. And solutions are often described by their concentration. Concentration would refer to how much solute is dissolved into the solvent. So if I pour a little bit of salt in here, it's not very concentrated. If I pour a lot of salt in here, it's going to become a very concentrated saltwater solution. Nifty. And there's a lot of different ways for measuring concentration. We'll look at that in the future. But for now, it's important to know that concentration is a thing. Well, solutions aren't always just things dissolved into liquids. In fact, sometimes, and more commonly interacting with us, there are things like gases dissolved into other gases. Air is a solution. It's a solution of oxygen dissolved into nitrogen. Holy crap, you're breathing a solution. Probably right now, unless you're somewhere weird or breathing pure oxygen. Anyway, another thing would be that chemicals can also dissolve into solids. An example of that came up earlier would be brass, which is a solution of copper and zinc. Also steel, which we interact with like all the flippin' time, well, that's iron with a little bit of carbon dissolved into it. Neat, neat stuff. Well, I want to wrap up this video, so let's do that right now. I hope you understand stuff about the conservation of mass and energy, and also understand a little bit about particle theory. Don't worry, we'll talk about it more in class. All right, dude? Ta-ta. Have a great rest of your life.